Okay, so picture this, a truck suspension, an electrical circuit, and 2 water tanks. I mean, what could those three possibly have in common, right? Well, it turns out they all speak the exact same mathematical language, and today we're going to learn how to speak it.
So let's start with a problem we can all relate to. A truck hitting a bumpy road. The whole goal is to keep the ride for the driver nice and smooth, even when the road is anything but. So how in the world do engineers actually model and predict something like that? It all starts with a really simple but incredibly powerful way of thinking. All right, the key to unlocking all of this is this one powerful idea, the input, process, output mindset. Think about any system, literally anything. Something goes in, that's the input. The system itself does something to it, that's the process. And something else comes out, that's the output. This simple framework is going to be our guide through everything. So yeah, back to our truck and that circuit. It still sounds kind of crazy, right? But believe me, they share this incredibly deep mathematical connection. Stick with me and I promise you, we're going to see exactly how. All right, first up, let's really get our hands dirty and break down the mechanical motion of our truck suspension system. We're going to build a mathematical model of it right from scratch. Okay, let's use our new mindset here. First, the input. What's going into the system? Well, it's the bumpy road itself, right? We'll call that X. The output is what we care about, the movement of the truck's body, which we'll call Y1. And that process in between? That's the suspension system doing its job, the mass of the truck, the spring storing energy, and the shock absorber or damper, getting rid of it. So, to translate all of this into the language of math, we're going to pull out a classic from physics, Newton's second law. All it says is that the sum of all the forces acting on an object is equal to its mass times its acceleration. Simple as that. We just add up the forces from the spring and the damper and set them against the force from the road. And what happens when you apply Newton's law to all these moving parts? Well, you get something called a differential equation. Now, I know, that sounds super intimidating, but really, all it is a mathematical sentence that perfectly describes how the truck's position and speed are changing from one moment to the next. Okay, here's the thing. Solving that differential equation directly, it's a huge pain. So engineers have this amazing mathematical trick up their sleeve called the Laplace transform. You can think of it like a universal translator that takes our really complicated time-based problem and turns it into a much simpler algebra problem in a new mathematical world called the S-domain. And after we do all that, after all that math, we get to the big payoff, the transfer function. I know, it looks like a crazy mess of letters and numbers, but don't panic. It's just a simple fraction. The output divided by the input. This one single expression is the complete recipe for how this truck is going to behave on any road you throw at it. Okay, you with me? Good. Now, let's just completely switch gears and jump into a totally different world, an electrical circuit. We're swapping out springs and dampers for resistors and capacitors. But as you're about to see, the math is going to feel very familiar. All right, let's apply that same input, process, output thinking. What's our input here? It's the voltage source, Vn, that's pushing the electricity into the circuit. And the output we want to measure? It's the current, I, that flows as a result. The process then is handled by the resistor, the inductor, and the capacitor. And remember how we used Newton's law for the truck? Well, for circuits, we have our own fundamental rule, Kirchhoff's voltage law. All this law says is that as you go around a closed loop, the sum of all the voltage changes has to be zero. It's the basic rule that governs our entire electrical system. And you're not going to believe this, but we follow the exact same steps as before. We write down our equation using Kirchhoff's law, we hit it with the Laplace transform, and boom, we get the transfer function for the circuit. Again, it's just the output, the current, over the input, the voltage. And just look at that. Doesn't that structure look eerily familiar? And this is the moment it all clicks into place. This is the big reveal. Just look at this. The damper in the truck, the part that dissipates energy, it's the mathematical twin of the resistor in the circuit. The spring storing potential energy, that's the capacitor. The truck's mass, which stores kinetic energy, that's the inductor. It's literally the same system, just wearing different clothes. Okay, that's pretty mind-blowing, right? To really hammer this point home, let's look at one more system, a hydraulic setup with 2 water tanks. You're probably thinking, no way this works for fluids too. Well, let's find out. You bet it does. We can break this whole thing down using that same input-output logic. The input flow to the first tank, Q3, causes an output, Q2, and that output becomes the input for the second tank. By By looking at them one by one, we can figure out the whole system.
And look what we have here. The same exact concepts popping up again. The little valve that restricts the flow of water, that acts just like an electrical resistor. We call it hydraulic resistance. And the tank itself, storing water, that's our hydraulic capacitance, just like an electrical capacitor stores charge. It's the same pattern.
So at this point, you can probably guess what happens next, right? We run the math, we do the Laplace transform, and surprise, surprise, we get another transfer function. This one connects the water height in the first tank to the flow rate coming in. Same method, same kind of result. It's a universal pattern.
Okay, so we've seen this transfer function pop up for a mechanical, an electrical, and a fluid system. We've done a lot of work to get here. So what's the big deal? Why is this one little piece of math so incredibly powerful?
Well, think of the transfer function as a system's universal fingerprint. It's this one elegant mathematical model that tells you everything you need to know about how that system is going to behave. And it all boils down to that one beautiful, simple idea: output divided by input.
And trust me, this is so much more than just a cool math trick. This is the secret language that basically all modern engineering is built on. It's why a mechanical engineer working on airplane controls can use the same math as an electrical engineer designing an audio equalizer. It's used to model economies, control chemical plants. It's how we design and control the incredibly complex world all around us.
So, from now on, when you look at, well, anything really, try to see it through this new lens. Ask yourself, what's the input, what's the process, and what's the output? Because you now have the key to a universal language that describes how so much of our world actually works. So, what are you going to use it to understand?